Today, last day of our gas unit. So you have a group quiz tomorrow, right? And then an actual test on Monday. The activity we're doing on Friday, if you're not going to be here, it's a no count. So just because you can't kind of recreate that experience. So if you have questions about that, you can ask me. We need to pick up kind of where we left off with talking about gases and kinetic energy and how it relates to something called root mean squared velocity. So this was the information page that's in your notes, but I want to just pull up a blank sheet and actually going to kind of show you where the root mean squared velocity comes from and where it's derived. So we know that average kinetic energy for a mole of molecules is equal to what? Who remembers the formula? It's got a 3 in it. 3/2 RT. So kinetic energy, average kinetic energy of gases depend on temperature only, right? Well, if we were trying to relate that to the velocity, say we want to find the velocity of the gas, we can set it equal to 1/2 mv squared, because we know that equation from physics, because that's the velocity of an object, right? But we don't want a velocity of an object, and we don't want to put in m for mass of an object. We want a mass of a mole. What in chemistry is the mass of a mole? Molar mass. So instead of a regular m, we're going to put in molar mass. And then instead of just a v, because they don't like v in chemistry for that, we're going to call it u, and we're going to square it. All right. So by setting these two equations equal to each other, we can rearrange and come up with that root mean squared velocity equation that you got last week. I want to get velocity by itself, that little u thing. So I'm going to multiply each side by 2. What is that going to do? It's going to be 3RT is equal to molar mass times velocity squared. Now what do I do to get velocity by itself? Divide by molar mass. So I get 3RT divided by molar mass is equal to velocity squared. And I need velocity, so what do? Square root it. And if I square root this side, I have to square root this side. So the actual root mean squared velocity equation is 3RT over molar mass is equal to the velocity. Okay? Now let's talk about units here and the importance of the use of R. In this case, we're going to use the energy R. Why we're using the energy R is due to the fact that this is based on kinetic energy. And so R is equal to 8.314 joules per mole K. Now, how does that give me the velocity? You might be wondering. Those of you in physics might know what a joule is. Have you looked at what the units of a joule are? A joule is a kilogram meter squared second squared. So if I have 8.314, that would be kilograms meter squared and then second squared. So that's the joule part, right? And then I'm going to put the mole K back. So if you look at this, we can substitute this in, and let's just put units in and show how this works. And what's really important, another unit we have to watch out for is this. Are we going to use grams per mole? No, look at your R. What are we going to use? Not grams per mole. We're going to use kilograms per mole. So I'm going to make this really big to give me room for all the crazy units. 3 times my R is 8.314 kilograms, I shouldn't even put the numbers in there, times meter squared over second squared times mole K, right? Times my temperature in Kelvin, whatever that may be, divided by, what's my molar mass going to be in? Kilograms per mole. So you have to divide your molar mass by 1,000. Now, that's supposed to be equal to velocity. What's velocity units in physics? What did you learn? Meters per second. Well, it's the same here. So if you look at the units, Kelvin cancel, right? Kilograms cancels. This is in the denominator, but it's in the numerator of the denominator, so that cancels that. This cancels that. What's the square root of meter squared second squared? Meters per second. So I just wanted to show you why we have to use kilograms and why we have to use the energy R. All right? So root mean squared velocity, Graham's law, kinetic energy, all that stuff uses the energy R, not the gas 0.0821 R. Are you good with understanding root mean squared velocity? So what's important about this, and this translates down here to my two characters. This is, have you all seen Austin Powers? This is Fat Bastard, this is Mini-Me. And I don't know if you've seen the scene in the lab where Fat Bastard's chasing Mini-Me, get in my belly, and Mini-Me is like zing, zing, zinging through all the chairs and tables. So the smaller the gas, the faster the gas moves. Mini-Me moves a lot slower than Fat Bastard. At the same temperature, they're going to have the same kinetic energy, right? But because one's so much larger than the other, you need more of that energy toward the velocity, so the velocity is going to be smaller the bigger you are. Does that make sense? Okay. So you can see here, velocity does also depend on temperature, but it depends on molar mass as well. As compared to that 3/2 RT, the only thing kinetic energy depends on is your temperature. So this leads us into deriving something called Graham's law. If you took pre-AP last year, you did this, but we made it a pretty little equation. You just plugged stuff in and you had no idea where it came from. Does anyone remember the equation? It was rate of 1 divided by rate of 2 is equal to the square root. Does anybody remember? Naira? Molar mass of 2 over molar mass of 1. You all remember that? So, and you would just, we'd ask you to compare two rates and you'd plug it in. You're like, yeah, I really didn't know what the hell was going on. We did teach you, though, the smaller it is, the faster it is, so you could see that correlation. But where this comes from is just a ratio of two root mean squared velocities. So if I have root mean squared velocity of gas 1 in ratio to gas 2, let's see what that looks like. Root mean squared velocity is 3RT over the molar mass of gas 1 divided by the root mean squared velocity of 3RT molar mass of gas 2. So you can see here that if we want to simplify this, we can get rid of the 3RTs because they're going to be constant. We're not going to be comparing gases at different temperatures. Our gases are going to have to be at the same temperature if we want to compare them. So that puts 1 over and 1 over. And to simplify, we can take this denominator and flip it, right? And so we get, as our final simplified fraction here, molar mass 2 over molar mass of 1. And that's equal to the ratio of the velocities. We called them rates, but it was still velocity, okay? So that's where it came from, and we're going to be using it again. So I just think it's in your best interest to commit to memory root mean squared velocity, Graham's law, and that 3/2 RT, okay? All of that will be useful. Not so much Graham's law, but they do root mean squared velocity in physics, but I think it's not till physics C. I'm not sure. All right. So calculate the average velocity of a sample of helium atoms at 25 degrees Celsius. So if we're finding velocity, what do we use? Root mean squared velocity. And what is that equal to? Just tell me the equation for practice. Over the molar mass. So we want the root mean squared velocity of helium. And so do we have a temperature? 3 we know. It's just the number. 8.314 joules per gram degrees Celsius. I'm not writing all the crazy units for joules, the kilogram, meter squared, second squared, just for room's sake. But y'all know why now, right? Why we need to have those units in there. And, oh, it's Kelvin. What am I doing? Moles Kelvin. I'm sorry, I'm doing a calorimetry thing in my head. Joules per mole Kelvin, might be. And then what is the temperature? I was doing specific heat units for some reason. I don't know why. 298 Kelvin. Right. And what is the molar mass of helium? It's 4 grams per mole. I'm putting grams per mole in there. What am I going to put? Yes, 0.004 kilograms per mole. And so you saw how the units worked. We're going to get meters per second here. So our root mean squared velocity of helium is equal to what? Give me some answers. Anybody? Anybody? Sorry, audience. Our class is a little slow today. Just give me 2. Yep, 1,400 meters per second. Is that fast? Yeah, because like a mile is 1,600 meters, right? Ish. So that's per second. And this is just at room temperature. So that's kind of the average velocity of a helium atom at a mole of helium atoms at room temperature. 1,400 meters per second. So yeah, our gases are moving pretty rapidly. It's kind of crazy to think about. Can you run that fast? No, not quite. Almost there. Okay. All right, oxygen diffuses at a rate which is 2.23 times faster than a sample of a reddish-brown gas. Determine the molar mass of the unknown gas. So with this one, looking at this here, we're comparing 2 different gases. So because we compare 2 different gases, you're going to need to do that Graham's law thing. They don't give us the rates, but I'm just going to write down. So we're going to compare the oxygen root mean squared velocity to this unknown, right? And so we're going to have the molar mass. What would go on top based on this setup? Of the unknown divided by the molar mass of the O2. Do you need to go somewhere? Okay. All right. So I don't have specific rates, but what did they tell me? One is 2.23 times faster than the other. So how can I translate that to something useful in my fraction? Yeah, this is 2.23 over 1. Whatever the rates are, who cares? This one is 2.23 times faster than that 1. All right? And so that's going to be equal to the molar mass I don't know. And what's oxygen's molar mass? 32. Now, whoa, we just put grams in there. Is that cool? Why is it okay now to do that and not in the last problem? Yeah, because it is a ratio here. So because of that, we can put in grams or kilograms. It's going to cancel. It's only because it's a ratio we're allowed to just put in grams. But do know whatever you put in here is what's going to come out there. So what is our molar mass? Before we do it, are we expecting this to be bigger or smaller than oxygen? Oxygen is 2.23 times faster than it. So that means it's going to be bigger and fatter, right? Oxygen is the mini-me in this analogy. So what is our molar mass? 59. Last period got 54. 59? Okay. And then the units on the velocity are, oh, it's molar mass. Dang it. Moles. Grams per mole right here. Grams per mole. So yeah, that's much bigger than oxygen. Okay, so does that kind of make sense? So that's all we're really going to do with Graham's law. It's just a matter of you practicing. When do I use kinetic energy? When do I use velocity? Coming next, this is an old AP problem. Consider 3 identical flasks filled with different gases. Flask A has carbon monoxide. Notice it's got a high pressure, but they're all at the same temperature. Flask B has got nitrogen, and flask C has got hydrogen. In which flask will the molecules have the greatest kinetic energy? They're all the same. Why? Same because they're at the same temp. And if you were answering this question on an exam, I'd want you to show that kinetic energy is equal to 3/2 RT and go, oh, they're the same temperature, therefore the kinetic energy is the same. Use those equations as proof. In which flask will the molecules have the greatest root mean squared velocity? Jot down what root mean squared velocity depends on before you even think about it. You know it's going to depend on temperature and molar mass, right? Temperatures are the same, so we're not even going to worry about temperature. Is pressure in there? They change the pressure on every example. No, so it's only dependent on, in this case, the molar mass. So which one's fastest? H2 is fastest. Why? And then you can go there. That's what that happens. All right? these are pretty easy once you get the concept behind them, okay? What's going to be hard is things like this next topic where you have to actually write some descriptions, and y'all are not comfortable with writing chemistry, and that's what I'm trying to get you there. So we have an equation. It's called the van der Waals equation. And the van der Waals equation describes non-ideal gases. So we've pretty much lied to you. Every time you use PV equals nRT, it's pretty much a lie because no gases are truly 100% ideal. So what we need to do is take a look at this equation, which is the true gas law we should be using instead of PV equals nRT. But the differences are so small mathematically, we really don't use it on a regular basis. You will never have to do math with this. You will have to ever use the van der Waals equation to kind of help you figure out what gas is more ideal than the other. And there's two parts to this van der Waals equation. Do you see that that is the ideal gas law equation? Do you see it? PV equals nRT. But it's got this weird stuff after each. Those are correction factors. Okay? When gases aren't ideal, there's two things that make them so, make them not ideal. The first one has to do with the volume. When you have a non-ideal gas, the volume is actually going to count. The volume can't be negligible. Here it says a gas particle does occupy space, and the higher the pressure, the more gas molecules are present, and the more significant their volume becomes. So in real gases, the volumes are more significant than they should be. So what do we want to do mathematically to get those volumes back to an ideal condition? We want to make those smaller, right? We want to subtract. And that's why this volume term is subtracted. What do you need to know? You need to know you subtract from the volume term because real gases have volumes that that can't be ignored. Real gas volume can't be ignored, so we have to subtract to compensate for that. Nobody's writing anything down. That's what you need to know. I need to see you writing some stuff down. You need to know this. You don't have to do math with it, but you need to know you subtract from the volume term because we're trying to compensate for the extra volume that real gases have. Does that make sense? All right. Yes. Yes. Which theoretically is increasing the volume of the so-called container because it's supposed to be a variable volume container. Right. Yeah, there is a pressure relation to it, but we're not there yet. We're going to talk about pressure now. So, pressure. Because we have to add this term, what this is telling us is that real gases, pressure is lower for some reason. And we have to add to that term to make the pressure higher. So what's making the pressure too low? Well, it has to do with the molecules and their attractive forces. Molecules ideally aren't supposed to have attractive forces in these gases because they're so far apart, blah, 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 but they actually do. And the bigger they get, the more electrons they get, the more attractive forces there are. If you're attracted to each other, do you see how that could decrease the pressure if the gases are attracted to each other? So the more the attractive forces, the more the attraction, the less the pressure. So we have to add a term to pressure to compensate for that pressure loss. Okay, does that make sense? So you're like, what are we going to do with this? I don't understand how this applies to anything I'm going to have to do. Well, you're going to see questions kind of like this. Explain in terms of the van der Waals equation why hydrogen chloride is much less ideal than hydrogen gas. I'm pretty much going to lay out the format for you. And you're just going to need to, and you can switch it up, put it in your own words. When you do practice that I'm going to show you online that you should do for a review, you can switch it up, but this is the general format I want. So they want to know in terms of the van der Waals equation. So that means you specifically have to refer to that equation. If we ask you this, we're going to give it to you. You're not going to have to memorize anything about the van der Waals equation. You're not going to have to sit there and remember which is subtraction, which is addition. We're going to give them to you. So you'll be able to refer to it. So I would start by saying, in the van der Waals equation, and I'm literally just going to write what I think you should say. Not that that's the only way to do it, but we add a correction factor to make up for lost pressure. Why do we have the lost pressure? Due to what's making the pressure go down? Attractive forces between molecules. So that's referring to the equation. Now let's take it to the HCl. What can you tell me about HCl? HCl, tie it to this, tell me about HCl, has more attractive forces because, okay, and I want you to use larger. Larger is correct, it's larger, but what makes things more attracted to each other with intermolecular forces? More electrons. It's the shift of those electrons. So HCl having more electrons has stronger attractive forces, making it less ideal. Okay, so you see I talked about the equation, and then I said, okay, well, now that we know what the equation is doing, HCl then, being larger, having more electrons, is going to have stronger attractive forces, making it less ideal. Make sense? Kind of the setup? So that's the one thing. What else do we have to look at? Why else is this not ideal? What was the first thing we talked about in the van der Waals? Yeah, in the volume. In the equation, let's talk about the equation. We subtract a correction factor to make up for additional volume due to the larger sizes of real gases. So that's the equation. How do we make it, tie it in? HCl is what? Is larger, and therefore less ideal. That would be enough for me, in my opinion, as to what you'd need to write. Okay? Yes? I need you to address both if both apply. Sometimes one will, well, no, I guess they both do go in the same direction. If it's larger, it's going to have more electrons. No, I want you to address both of them. Unless this question says, of the two, pick one. Just read the instructions. Okay? And the fact that these are so distinct, that's when it's much, much less ideal. Okay? It's not like we're comparing helium to hydrogen. This is a pretty significant difference in ideality. Okay, so real quick, let's see if I can get this caught on video. You guys are going to need to get ready for your group quiz tomorrow. On the website, whoop, that would be my mail. On the website, you have a review sheet that is a really good practice for free response problems, because that's where I think you're going to need the most practice, since that's the most new thing. So here under Unit 3, do you see where it says extra problems with answers? If you view that, when we used to hand out everything in paper, we'd give this particular paper was to be cut in half. So just know that it's the same 3 questions on bottom and top. Try to work these cold. Answer them as if you were taking the test. Wait to do this until you're really studying for the test. And then go down and grade yourself and give yourself points. The first one's 6 points, 9 points, and then 3 points. And see how you do. Okay? Just know that using van der Waals equation, know that it's going to be given to you, so don't try to memorize it, okay? All right, so I kind of expect you to do that on your own for your own review, and then come in and ask me questions. That's it.